Assalamualaikum everyone. So today we are on lecture 12 in EE341 microelectronics. So what we are going to do today, we're going to continue from the last lecture where we started the frequency response, and we're going to build on top of what we have learned in the last lecture, and we'll see some further concepts which are related, but yet they try to give us some further grasp that how we can intuitively solve the problems or see the frequency response of system by just analyzing the circuit. Last time, just recapping what you have done, you have seen, okay, you write a transfer function of a overall response, and from that transfer function you find, okay, how the response is of a specific amplifier is if it is going like a low pass configuration, then where this cutoff frequency was coming, and that cutoff frequency was ultimately pole of the amplifier. And when we say pole, this means it's related to some capacitor, right? And similarly, when if there is some further reduction, for example, and this node is further going down, this means second pole is coming here, and the second pole is also one of the capacitors. So these poles are basically locating or mentioning the capacitors in a circuit. And if you recall, you have seen an example of a basic, even started with the common source configuration, which was somehow similar to this one, and we can even start with the same example that you have seen. Okay, if you have some load RD, and if you have some capacitance which is connected to the load CL, and this is also the point V out, and here it is V in, and here VDD. So you write the overall transfer characteristic, and you see, okay, you can do the magnitude characteristics and also the phase characteristics. Definitely you focus more on the magnitude characteristics, and you write the overall transfer function was somehow, or overall relation for the V out when you consider the CL was minus GM, if this is M1, it was minus GM1 times, it's also V in was coming here, and RD now is in parallel with something which is because of this capacitance, and that is a reactance CL times S. So you are talking in the form of S domain. And you say, okay, this S can be represented with the form of J omega. And if you translate back, that's reflect back into something. So, but the important thing was that in this configuration, we didn't have two poles because we only showed one specific, just let me go back. Yeah, one specific pole, and that one specific pole was basically ultimately this point was linking to, or omega P1 was linking to something which, if you recall, was related to this RD and this capacitance, RD times CL. So that somehow we need to write the complete transfer function of the system, and then we can just derive, okay, which one is affecting what. But when we want to analyze the circuits, we don't want all the time to do that transfer function and we reach the same conclusion. We are engineers and we want to intuitively see the circuit. Okay, I am representing this circuit. What is the dominant frequency? What frequency is affecting me? And if I want to reduce or increase the frequency, what I should do? So as an engineer, you need to see, okay, which capacitance is basically affecting this, for example, the first pole, and then you can tweak that thing, because this first pole is ultimately the 3 dB frequency of the system. And if you can reduce it, then what's going to happen? Your frequency or your bandwidth is going to be reduced. Similarly, if you bring that on the wider side, if you have something like this pattern, what's going to happen? Your frequency or bandwidth of your system is increased. And what it is depending upon in this configuration is depending upon two things. RD and load capacitance. What is RD? Output impedance. And what is load capacitance? The capacitance which is seen at the load. So now we know that if I want to increase the frequency of the system, I have to increase, I have to reduce basically either CL or RD or both of them, and vice versa happens for reducing the bandwidth. So it tells you one notion, but that's only for a very much simple circuit. If the circuit starts becoming complex, we need to know some techniques that how we can do that thing. So we are going to analyze those techniques in today's lecture. So coming back, what are those techniques? Last time, definitely you have seen the border plot. The border plot is very much strong, very much robust for magnitude and phase plot of the transfer function, and it gives you complete depiction in the frequency response. And that is used when you have both your overall transfer function is available. So that is one alternative, but we are not going to do that in today's lecture. Rather, we are going to analyze that how we can utilize those poles, these omega P1, omega P2, whatever the number of poles, intuitively by just analyzing the circuit. One thing we just got to know, if we have seen this common source configuration, the pole was linked to this capacitance and this impedance here. So this pole has some relation with this capacitance and resistance. And what is that relation? It's inversely proportional to product of impedance. I'm just writing a resistance and a capacitance. So your pole, ultimately, whatever the configuration, it can be like any configuration, it can be not on the low input side, it can be output side, intermediate side, whatever, it comes out to be that the pole is inversely proportional to product of resistance and capacitance. But the important thing is that what are those resistance and capacitance? So those resistance and capacitance are basically the node points, like any node which forms a capacitor from that node to the ground. Similarly, any point at that node which makes up resistance from that node to the ground. So if we can find that point, we can say ultimately we can find the pole of the system at specific node. So how we can define those things? So we can just unify that stuff that, okay, we talk about this inverse relationship, but the resistance should be output or any node, and its value to the ground or AC ground, if I say explicitly, since we are talking in terms of small signals, so we will talk about AC ground. And similarly, any capacitance at any node and its value to the AC ground. And this should be in the pair. So for the same node, if we are talking about this node, so we will see, we want to talk about this specific node. If I say 1, so the capacitance from this point to the AC ground and the resistance from this point to the AC ground. Again, you can say this VDD in the small signal is going to be an AC ground. So we want to talk about this capacitance product with the product of this resistance. We're going to see some other examples which will clarify that, okay, if the capacitance on input side and if the intermediate side, how the things are going to behave. But in totality, in general principle, we need to know this thing. And if we want to generalize that stuff, so we can say a small signal RJ resistance. So it's a resistance RJ at node basically J. I wrote 1 there, so at node J to the AC ground. And a small signal capacitance Cj again to the AC ground. So product and inverse of this one at every node is going to depict one pole. If you have multiple capacitance, your system is going to have multiple poles, and multiple poles will result in multiple first pole, second pole, third pole. Each pole is going to add minus 20 dB per decade, minus 20 dB per decade, minus 20 dB per decade, right? So we can utilize a generic transfer function formula, which might be you have seen in the last lecture or your feedback course, that h of s, any transfer function, is ultimately equivalent to low frequency gain, or we can normally call mid-band gain, or a DC gain, meaning you can write, okay, a mid-band gain can be A naught, yes, A naught times 1 plus S over, or let me write the correct terminology which we are going to use in our system, omega over omega Z1. Zeros, because there are zeros too, which are going to come later when we're going to talk about two-stage amplifier. Product of 1 plus omega over omega Z2, and there can be multiple zeros too. So the not plus is going to be multiplied, divided by, and the number and the poles. The poles we know are because of the capacitance. This is basically the expression. So we got to know one thing. If I know my DC gain, which we were doing in our previous content till now, first lecture 10, we were finding the gain of the amplifier. So if we know the gain of the amplifier and we know the node locations, we can find the explicitly capacitance at that node multiplied by the impedance seen at that node to the AC ground, and we can find the omega P1, we can find omega P2, and we can just plug it into this formula and it will give us complete information about the circuit in terms of its frequency, how it's going to behave. Okay, when is going to cut off going to happen, at what frequency the system is going to behave like an open loop, at what frequency the system is going to pass the signals. So it will depict all the information with the help of this transfer function, and that we can just see by analytically. So we can just analyze this thing using some examples, and then we can proceed further. So if we talk about an example of a little bit complex circuit, again, it's not much complex, but a little bit complex circuit, which can just give you this rule, how you can apply this technique. And I will write some bullets also. So for example, you have Vin being applied here at source impedance RS. So it's a source impedance. It's not the gate impedance because that is going to be infinite, but we have a source impedance. You are using, for example, a signal generator or any cable which have a resistance to be called source impedance RS. Then we have input capacitance here, just to mimic that the impedance is not just because of the output load. There can be multiple capacitance or multiple nodes. And then we have, so it's again a common source amplifier to unify the things. M1, name of the transistor. So here we have CL, again the load. This node is the V out, as in the common source configuration. Input is on the gate, output is on the drain of the amplifier, and here we have some load VDD. Similar to the previous example, which we have just seen, that lambda is equal to 0. So if lambda is equal to 0, we can say R01 is equal to infinite. We are not much, even if it comes, it's not affecting us, but at this moment, for simplification, we want to evaluate in this way. So what we want something like this. We want the overall expression H of S, or to be more accurate, we want H of omega of this system, which is going to be something A naught, the DC gain, times 1 over, again, we are not going to concern about the zeros at this stage, that in the later two-stage amplifier configuration. I'm going to talk about those ones, but currently we want to talk about the poles, and we can identify the number of poles by number of capacitance which are in the signal path, or the number of nodes with the capacitance in the signal path. So number of poles will be equivalent to capacitance at independent or distinct, I would say, not independent. I will just tell you what does this mean, so that's very much important. Capacitance at distinct, and I will clarify this point, distinct nodes in the signal path. Okay, signal path. So दो चीजें हैं इसमें. First thing, the capacitance should be distinct. If I say there's a CL, and if I say at this node there's another capacitance, which is I'm giving an MCB, so I'm going definitely, if they are parallel, I will consider it as a one capacitance, and I will use it CL plus CB because they're in parallel, right? That's one thing. So very much important. They should be distinct. If they are not, I will consider it as a one capacitance if they are in parallel. And second thing, they should be in the signal path. I'm concerned about those capacitance which are going to affect my output, not those which are not in the signal path, right? If, for example, if something is related to the current mirror and is being signal path, means input is coming from here, it's going this way, this way, this way. So this capacitance C in is definitely in the signal path. This capacitance CL is in the signal path. Any other capacitance at this moment, even if it comes at this moment, if it's not in the signal path, it's not going to be counted. So we have two capacitance. They are distinct. They are in the signal path. So I'm going to consider two poles. So I can explicitly write, I am concerned about omega P1 times 1 over omega P2. And as I mentioned, we're going to not consider zeros at this stage. So zeros are not there. I will just explain when and why they come. But at this moment, you can say zeros are not going to be playing any part in the configuration. ठीक है? तो हमारे पास दो poles हैं which we can see. So let's relate these omega P1s and omega P2. So पहला कौन सा है? Let's talk about this. Say this is omega P1 node. So इस पे capacitance क्या है? The capacitance is C in times something, that is an impedance. Impedance क्या होगी? We mentioned about from the node, this is the node point. Let me use a different color. This is the node point to the AC ground. C in है times, this is going to be treated as AC ground in a small signal. So this means C in times RS. So omega P1 will be C1 over C in times RS. Similarly, omega P2 क्या होगी? 1 over, again, let me use a different color. This is a node point CL times, what is this resistance? RD, and this is again an AC ground in a small signal. Times RD जो हम लोगों ने अभी देखी थी. तो omega P2 is 1 over CL times RD, since lambda is 0, R01 is infinite. So I can explicitly write these things that h of omega is equal to A0 1 over 1 plus omega divided by C in times RS times 1 plus omega divided by CL times RD. That's good, but still I don't know A0. But that's what we were doing in the first 10 lectures. We know how to find the gain of this amplifier. And what is the gain of this amplifier? It's going to be A0. It's a common source, simple. R0 is infinite minus GM1 RD. minus because it's an inverting amplifier. So we just plug it this way. But when we're going to talk about magnitude, it's not going to do anything. It's going to come only in the phase. So we can write minus GM1 RD times or divide by 1 plus omega C in RS 1 plus omega CL RD. So this is the overall frequency response. If I want to plot the magnitude response, we can easily plot. Magnitude, everything is going to be mod. So this point will be somehow GM RD or 20 log this value, whatever the value you want to represent in the dB or whatever the scale. So this is going to be starting point. Now we have two poles. So we need to see omega P1 is this one or omega P2 is the one which is going to come first. So that's something which we need to see, okay, which is going to be dominant. Dominant is the pole which is going to come first, meaning if C in RS value is bigger than CLRD, if CLRD is going to be bigger than value, this means 1 over CNRS will be less than 1 over CLRD. So in this case, if CNRS is bigger than CLRD, this means that inverse of this one is going to be less than the other factor. So we need to identify which is going to be in our configuration, which is going to be the dominant one, and then we can see which one is going to affect ultimately the configuration. But the rule of the thumb is that normally this is not going to be true. This expression is not going to be true. Most often my CL is a bigger value as compared to Cin, and my RD is a bigger value as compared to RS. So all the time CL product of CL and RD will be bigger. That's why ultimately 1 over CL RD will be less, and that will be the dominant. Dominant मतलब जो उसका edge decide कर रहा है, which is deciding its edge कि कब ये point आना है. So this is going to be omega P2, and somehow later on this thing is going to come, which is going to be omega P1. So यहाँ से it's going to be minus 20 dB per decade, and then we have minus 40 dB decade per decade. Okay? So that's somehow which we are now familiar with the things how we can do. So this is again a simple configuration which we just have seen, and in the simple configuration we can directly apply the same rules which we have learned. We know how to find impedance at a specific node. We know how to find the gain of a single stage amplifier, and we can just directly multiply that impedance with the capacitance and plug in this formula based on number of poles which we are having. So if we just want to generalize some rule of thumb, and we can apply into another example to have a complete feeling of the things how we are dealing the stuff. And just to reiterate, the overall expression in the previous one will become if we want to talk about magnitude plot phase, we will see in future lectures. Then we will discuss more about the phase too, because phase is very much important. So I'm just talking about the magnitude response, so I get rid of this sign. So we can directly write 1 over omega squared divided by omega P1 square, and we can just plug in the omega P1 values as we calculated. I'm just not plugging it, but you can plug it again the way. So again, what is this 2? So omega P1 is equal to 1 over RS Cin, and omega P2 is equal to 1 over RD CL. Okay? So you can just plug in these values and you can figure it out. So the rule of thumb to find the poles, what we need to do, that's important. Find poles, first thing is the resistance, or locating the number of, let me write, locating number of distinct nodes with caps. Because जब तक capacitance की value ही नहीं होगी, we cannot find out. So we need to have a capacitance value. Then find resistance from the node to AC ground. Third, find capacitance. Sometimes it can be combined, so you need to find the node to the AC ground. Fourth, the product of R and C and take its inverse. Okay. So in this way, we can find the overall pole for any system. Okay. So we can apply to another example to see the common gate configuration, how it's going to work, and then we can see variant of those things. At this moment, we are talking about only those capacitances which are just coming from a node to the AC ground, but there can be some capacitance in the middle. How we are going to deal those situations, because they also come. So let's just talk about common gate scenario, and then we can move on towards a different scenario, and we can apply a powerful concept of a Miller capacitance. Okay. So let's draw the circuit of a common gate. So here we have an input capacitance C in. We have here an NMOS. So the input is on the source, the output is on the drain. So that is a common source for a common gate for us. Load capacitance, and here we have again something RD, and it's in a VDD, but it's an AC ground signal. Okay. So I guess this circuit is clear. Input is here. The two capacitances, meaning we have ultimately two poles. So we can write H of S will be equal to A naught divided by 1 plus omega by omega P1 times 1 plus omega by omega P2. ठीक, तो ये तो हम लोगों के पास पहली चीज हो गई. And what we know about omega P1. Just again, if you are at this point, I would highly like all of you to pause the video and just try to find yourself what are the two nodes and what are the capacitance there, and then what are the resistance there, because then it's not going to be helpful if you don't pause the video. So first thing, definitely the pole is at this point. First pole, this is the first node, and this is the second node. So I will write first and the second node. So at the first node, I'm calling it omega P1. We need to find some, let me call it an R Thevenin. Again, just I'm giving a name, and C. C we know from this point to the ground, or to the AC ground, or the DC ground even here, C in. And what is this R Thevenin, or the equivalent? Let's not confuse with R Thevenin. Rather use an R equivalent resistance, because Thevenin we then mix with the other concepts. R equivalent. Okay. So R equivalent. So R equivalent is equal to what? So we have this point as AC ground. If I just want to mimic this point, so ultimately this is the node. Again, this is the one node which I'm writing. One. So here the capacitance is being here. So this is the capacitance C in. We have here RS, and here this is an AC ground again. Okay. So this is a small signal. This is going to be an AC ground. And what's happening here? This is the source of this NMOS. So if I see from the source point, I normally see what impedance? 1 over GM1. So it's going to be 1 over GM1. 1 over GM1. And then it's going to be, this is the impedance which is seen here. And I am seeing the impedance at this point. So what will be the impedance or R equivalent? R equivalent will be parallel of RS with 1 over GM1. So RS in parallel with 1 over GM1. Make sure you got this message clarified. So omega P1 will be equal to 1 over RS in parallel with 1 over GM1 times Cin. And omega P2, that is straightforward, the something similar which we have seen. This is the node 2 and node 2 CL times RD. So 1 over CL times RD. Again, we are assuming lambda is equal to 0. This means R around 1 is going to be infinite. So now we can plug in into this formula, but we can find also A naught. It's a common gate configuration. So we can find out the gain. So let's say this point as a Vx. So my V out, let's see. So V out over Vx will be equal to Vx by V in. Okay, I say this node 1 as V in. So what is my Vx by V in? The Vx by V in is voltage division simply happening. Again, 1 over GM1 divided by 1 over GM1 plus RS. And the other one, we all are familiar now, V out by V in. So this is V out, not V. Oh, let's write complete. V out by Vx. Yep. V out by Vx from this point to this point. So we are talking about this point and this point. So now we all know it's a common gate. It's going to be non-inverting amplifier. So we can write simply, and again, R01 is infinite, GM1 times RD. So A naught here is GM1 RD times, I'm not like opening up and doing that math, which you can easily do, 1 over GM1 plus RS. So we just need to then multiply or place in this thing omega P1 and omega P2 in this configuration, and we can just get to know about the frequency response. So that's like make our life easy if you just do all this analysis by using the transfer, taking the parallel configuration there, then the overall scenario will become complex. And you can see this is for a single stage amplifier. If I talk about multiple stages amplifier, which you will just see a glimpse now, then the design will become or the analysis will become more and more difficult. Right. So if we want to move further, that now we have seen those scenarios where the capacitance at this moment is just at a specific node, and it's basically linked to the ground. So that's easy. We know that we just need to find impedances. It's just one notion. We need to know that, okay, we need to apply the equation, but nothing else new. But what about such scenarios? I'm going to just draw now. If you have such configurations, this is a VN, this is an RS, okay. And so you have again a common source configuration. Like a VDD, RD, and there is some capacitance which is connected between the gate and the drain. And this is V out. And I'm calling this capacitance the CF, the feedback capacitance. So you might say, why it's going to happen? This is the common scenario. This is a parasitic capacitance. This is a parasitic capacitance which comes all the time between the gate and the drain. And that's the reality. We have to live with that. So what should I do with this scenario where both the nodes are tied to, or both the terminals of the capacitor are tied to specific nodes? They are not tied to the AC ground anymore. So what should I do? So that's like a problem which is in hand, because what we know to solve the scenario is that, okay, one node should be to us, one terminal should be at a node and the second terminal should be AC ground. But this cannot be possible in such scenario. So for these cases, we need to look into some other phenomena, and that phenomena was basically sorted out by Miller. Miller was a person in 1910 almost. Yeah, in 1910, early 19s, he was. So he gave a concept, not for this specific scenario. He applied this concept for another problem, which he said, okay, if I want to find, he just talked in the form of impedance or a resistance. Let's say he has this impedance ZF, two terminals A and B. And if we want to represent these two terminals in this fashion, this is A to ground, and this is B to ground. So he want, okay, how I can link this Z1 in terms of ZF? And that's something similar problem. We have some feedback capacitance, which is basically between two junctions, and what we want them to be independent with respect to ground. If we can have that relation, it will make our life easy. So what he did, he have this scenario in hand. He said, okay, if I want to keep the voltage, like this is VA from this point to this point, and from this point to the ground VB. If I want to keep the current which is flowing from this terminal same as here, so I at this point, let me say I is same as this current, not I1, it's an I. So this current is the same as this current. So if I apply this thing, then what will be the value of Z1 and Z2 in the form of ZF? That what is all we want to know, because CF is known value. We want to know the different value which we want to get for the Z1 and Z2. So let's try to do that math, and then we can apply into this circuit. So for example, since the current is the same, so the I can write will be equal to VA minus VB divided by ZF. Okay. Again, I'm writing I1, so it should be I. Because I'm used to write I1 or I2, so it's difficult. I. And that will be equivalent to the current which is flowing from this node, because again, this is V1, VA divided by ZA, which will be also equal to ZB, or will not be equal to ZB, rather will be equal, because that is the opposite current flowing through this junction, that's on the opposite side. So that current will be on the opposite side. So this will be equal to minus VB by Z2. Okay. So the current sign is going to be present. If we just want to take these two things and if we want to represent Z1, so we can write Z1 will be equal to VA times ZF times VA minus VB, right? We can just write in this formation, and we can do this thing VA, and if we just take VA common from both sides, so VA is here. If I take VA common, it will be 1 minus VB by VA, right? 1 minus VB by VA, and what it is depicts, this VA will be cancelled, and I will be left with ZF 1 minus VB by VA. If you see this scenario, what is VB by VA? It is ultimately gain which I am getting. So I can write in this scenario, ZF will be equal to the gain, the voltage gain, AV I'm writing, going from this point to that point. So Z1 can be simply written as, if I know the gain, I can write the values. And similarly for Z2, if we just plug in, it's going to be a little bit different, but the expression will be ZF divided by 1 minus 1 over AV. So what it is telling us, the information, Z1 will be enhanced. This will be increased as compared to ZF. Is my gain is negative. Okay. Positive gain nahi hona chahiye. Positive gain will not work. All the time we want a voltage gain to be more than 1. And if it is positive gain, what's going to happen? Ultimately, the resistance is going to be negative. That is not possible. So all the time the gain AV should be negative. This means it should be in inverting configuration. ठीक है, जिस तरह हमारे पास है, it should be in inverting configuration, and the Z1 will be enhanced, will be increased. On the other side, Z2 will be decreased or will be having a smaller value as compared to ZF. So this is the information which we are getting. And again, the same thing, AV should be a negative or an inverting configuration value. So let's apply this one to the capacitance. At this moment, we have applied this to the resistance, and we know resistance and the capacitance have just inverse relationship. So we can directly apply this thing to capacitance. किस तरह apply कर सकते हैं? Let me just write the same expression. We just wrote Z1 was equal to ZF divided by 1 minus AV. So if I want to reflect this or reflect back to the capacitance, my capacitance will be 1 over C1 will be equal to, I will just show you how it's all happening. 1 minus AV times CF, where AV is equal to all the time negative. So I can write this thing 1 plus A naught CF. Now let me recreate the circuit and then we can just see all the things. Again, make sure if something is not clarified, go back or come in the office hours or in the class time or anytime you can just send an email and we can schedule. But make sure you clarify this point, because this is again a simple but a very much strong that use a lot even in the old time, but nowadays this concept is used a lot in a different configurations. Okay, so you have RS. I'm redrawing the circuit again and then we'll redraw the modified form. So we have V in here, we have a capacitance here, which is CF, we have an RD here, we have a ground here, we have a CL here, and we have a V out here. Okay, and this is the VDD. So following the Miller theorem, we normally call this Miller whole analysis, which he did as a Miller theorem. We can represent the CF in two capacitances, one at this node, which is node 1, and one at this node, node 2. Each of these capacitance will be connected to this node and the AC ground, and the second capacitance will also be connected to distinct node 2 and a AC ground. So I can represent this in this fashion. V in RS. So I'm writing this as C1. Okay, so this capacitance, I open the Miller theorem. Now CF is not anymore. I have here RD. I have here C2 in parallel with CL. So these two are not distinct. So now CL plus CL2 will become one node capacitance. So this is one node and this is two node. And C1 की वैल्यू क्या हो जाएगी? इसका गेन हमें पता है. इस गेन is equivalent to AV क्या है? Minus GM1 RD. Again, R naught is infinite. So I can find that C1 will be equal to, it's going to be increased value 1 plus GM1 RD times CF. ठीक है, and C2 की वैल्यू क्या हो जाएगी? C2 value will be something which we just figured out, that C2 will be equal to 1 sorry, yes, that is C2 will be equivalent to, we just need to plug in this value. Oh, C2, let's write, we didn't write it here, let me write it here. So Z2 was equal to ZF divided by 1 minus 1 over AV. So if you want to write in the capacitance, C2 will be equal to, or 1 over C2 will be equal to 1 over CF times 1 plus 1 over A naught. And usko pehle hi, the C2 will be equal to CF times 1 plus 1 over GM1 RD. Okay, so the C2 will be very much slightly enhanced, almost negligible, but the C1 is going to be enhanced significantly based on the gain of the amplifier. So अब हम क्या कर सकते हैं? We can find omega P1 and we can find omega P2. Omega P1 क्या है? 1 over C1 जो हम लोगों ने एक्सप्रेशन फाइंड किया था, C1 times what is the impedance here? RS. Omega P2 क्या होगा? That we just need to see. It's going to be CL plus C2. Again, the C2 जो हम लोगों ने find किया था times RD. And the gain is there, so we can directly plug in the transfer function and we can find the overall transfer function for this configuration. So again, this is a very much strong but intuitive and helpful approach. So that which is normally called a Miller theorem, and this CF is known as a Miller capacitance. So this is commonly known as Miller capacitance. And this whole theorem is known as Miller theorem. Okay. So moving forward, now we know this thing. It can be applied to inverting amplifiers. It can be applied all the time whenever the capacitance is between, or resistance is also in between two nodes. So we can write the gain should be inverting. So we can write this thing V in. There should be, whenever there is something in the middle between this V in and V out, CF, we can directly map, and it works, into two capacitance C1, which is 1 plus A naught CF, and another capacitance C2, which is equal to CF times 1 plus 1 over A naught. So this is not going to be any significant A naught will be value, so equivalent to CF. But the main thing is that we get a huge increment on this side. So is the we can figure it out any value whenever some capacitance in the middle, and we can form it, or we can draw the transfer function of the circuit. So we'll do one last, I guess, example, and then we can conclude this lecture. And what I would highly like all of you to go through this, and then we can build on top of it. We can talk about some journal frequency responses in the next lecture to get a more clear picture, and we'll conclude this frequency response. So another, I guess rather that example is somehow similar, which we have seen. The example, we just did somehow that example, but make sure to do this example yourself also, 11.10 from your book. So since it's a chapter 11, so 11.10 example, which is talking about the same thing, that okay, if you have some similar configuration, which we just drawed, RS, V in, you have a Miller capacitance called CF, you have some load RD, you have some load capacitance CL, and this is your V out. And now the lambda is not zero. So you can just assume now you have also, if it's an M1, you have RO1. ठीक है? So now जब आपके पास gain होगा AV, that will also equal to minus GM1 RD in parallel with RO1 हो जाएगा. Your omega P1 will also be equivalent to 1 over RS times C1, CF, but now CF, so CF times 1 plus GM1 RD in parallel with RO1 हो जाएगा, and your omega P2 will be equal to 1 over RD in parallel with RO1, since now you have to bring this thing, and it will be equal to CL plus CF times 1 plus 1 over the same this expression. GM1 is only under this one, so but I don't have spaces, so I'm writing in this fashion. Okay, so you can just have this thing, and then you can plug it back into the overall HFS, and it's all already solved in your book in example 11.10. So you can do that this one scenario and get an idea. Also in your book, a little bit intuitive way of this Miller capacitor is also explained. Just go through that one, that how the capacitor change is happening and why this capacitor and the input side enhances as compared to the intermediate. What is this magic? Ultimately, it's a magic and it's used a lot, but the whole idea what happens that any change which happens at this node, for example, delta V, it increases the same amount of delta V out, and that is reflected in the form of a capacitance increase if you just want to see with respect to the ground node. But the concept is very much, the overall concept is very much strong and it's used a lot, as I mentioned. So make sure you go through that thing, and we will meet you in the next lecture. And by that time, go through the content. If again, any concern, any questions, raise a query, yeah, or you can approach in the office hours. Office hours, we are available in person too. So you can just, if you have some issue, you can directly tap in. Okay. Thank you for attending and listening to the lecture. I will just stop the recording now.